Good afternoon, and thank you for calling into this workshop. The title of this session is Accelerating AI on the Grid. And over the next 3 hours, our goal is to connect you with information and with resources that will enable you to begin analyzing grid data, both on the job and in your research. We'll give you a crash course on how to interpret the data, and we'll demonstrate a few applications that have been developed to date. Our objective is to build awareness about some recent advancements in the technologies and analytics and application of grid data, and to paint a picture for how more widespread data collection and analysis could begin to change the way the industry operates. This workshop is part of a broader initiative called NI for AI, which I'll be describing in more detail in a couple of slides. I want to start by going over the agenda and by introducing our panelists for today. I am Laurel Dunn. I'll be giving a relatively short talk about how this workshop fits into the broader NI for AI initiative, and we'll point you to some of the resources that we're generating that will allow you to put concepts from this workshop into practice, either on the job or in your research. I am also a PhD candidate at Berkeley, and I specialize in data-driven decision analysis for electric power systems. Next up, we'll have Sasha von Meyer, who is a professor in electrical engineering at UC Berkeley. She'll give a talk about the fundamentals of PMU data, and will help you build some intuition around what the data mean and how you can apply it to understand different dynamics that are happening on the grid. She'll hand it over to Kevin Jones, who works at Dominion Energy. Kevin is a practitioner in industry who has worked extensively with PMU data on the job, and he'll be sharing lessons learned and case studies from PMU applications that have been developed at Dominion. Next up will be Sean Patrick Murphy of PingThings. PingThings is a startup that has developed a data analytics platform that Dominion and other utilities use to make it easier for analysts to interface with time series data on a day-to-day basis on the job. This is the same platform that underlies the NI for AI ecosystem. Sean is the CEO of PingThings, and he'll be talking about the power of data, and will be painting his vision for AI in the industry. Next, we'll have Mohini Baraya, who is a PhD candidate at UC Berkeley in electrical engineering. She specializes in analyzing PMU data, and she will be describing an algorithm that she has developed for detecting voltage sags using distribution PMUs. Finally, we'll hear from Miles Rush, who is also a PhD candidate in electrical engineering at UC Berkeley. He specializes in machine learning applications for PMU data, and he'll be talking about the frequency of the grid and how we can understand and analyze frequency given phase angle measurements recorded by PMUs. With that, I want to give you a little bit more context about NI for AI. NI for AI is short for a National Infrastructure for AI on the Grid. We are a 3-year ARPA-E project funded under Open Innovation 2018. And the objective of the project is to advance the use of artificial intelligence in the industry. The approach that we're taking is to eliminate any and all barriers that have historically prevented people from readily working with grid data. The project has 3 pillars. The first is to provide access to a state-of-the-art data analytics platform. This is PingThings Predictive Grid platform, which was developed to handle large volumes of time series data from dense sensor networks and make it easy for analysts of different skill levels to readily interact with and interface with the data on a day-to-day basis. This platform is becoming available for students and researchers and anyone to use to analyze and develop analytics using the data that the program is hosting. And the second pillar is the data themselves. We are creating open access data sets that anyone can readily interface with and use. These data are designed to capture real-world dynamics on the grid that are relevant to developing analytical tools that answer questions industry practitioners are faced with. The third pillar is to build up a community of analysts and practitioners that are committed to advancing the use of data and developing new analytical tools for the grid. To put this in context, let me tell you about some of the data sets that are currently available to you through the platform. First, we have real-time data sets collected by a network of 5 streaming sensors that are deployed at different locations across the country. This is just an early deployment. We're currently in the process of disseminating more sensors to get broader coverage of the national grid. We also have point-on-wave data, including an experimental data set collected by a university in Switzerland called EPFL. They installed 3 point-on-wave data sets on a distribution feeder and recorded high-frequency measurements for 6 charging and discharging events of a battery energy storage system. We also have data from wide area sensor networks, including a network of 23 sensors on the transmission grid. This data set includes 3 event snapshots for 2 switching events and an oscillation, and can be used to study how these dynamics spread and propagate across a broader geography of the grid. Last, we have archived data from a distribution PMU pilot program that ran over the course of 18 months. This involved installing 6 micro PMUs on 3 distribution feeders, including 1 feeder that has a sizable PV array. You'll see analytics developed using the sunshine data presented in a couple of the talks today. The project also features a blog which offers several opportunities for you to learn more. We have deep dive tutorials that will elaborate on some of the concepts covered in this tutorial, as well as others. We have exercises designed to get you to start programming and start asking questions of these data sets. We offer code, including some of the code underlying talks that you'll hear today. And we'll be highlighting research advancements in this field. We'll share new ideas for research that the industry needs done. And our goal is to provide thought leadership around the use of AI in the industry and opportunities for advancing that work. You'll also see updates about events that we're hosting and where you can find us giving talks in the future. I'll close this portion of the talk by sharing a few ideas for how you can get involved in NI for AI beyond the scope of this workshop. First and foremost, we encourage you to use the platform and analyze the data in the interest of advancing your own research. If you have access to data or are collecting data that could be beneficial to make available to others who are using the platform, we encourage you to get in touch about the possibility of sharing your data with us. We are also in the process of deploying sensors and are recruiting sensor hosts. As a host site, we can work with you to site sensors in a way that will collect data that captures dynamics that are interesting and valuable to you, either in your research or in operating your grid. We'll be hosting data competitions. We invite you to participate and to spread the word. Feel free to reach out and ask questions. And we encourage you to build up a network with others who are doing work in this space. There's a really large body of academic research and applied work happening in the industry towards advancing the AI tools for utilities. We encourage you to follow work that's happening and build collaborations with others. One of the key advantages of the platform and of working with open source data is that it makes it incredibly easy to share information and share results and share code across collaborators at different institutions. So we encourage you to capitalize on the platform in that way. Also, please reach out and tell us about your work. We have an active body of stakeholders in industry that are following the project, and our hope is to use NI for AI as a pathway for spreading information about research that's happening in this space. If you have other ideas for how you can get involved and advance this initiative, we encourage you to reach out and share your ideas as well. You'll find contact information and a link to subscribe to our newsletter at the bottom of the slide. With that, I suggest that we jump into the meat of the workshop. I will hand it over to Sasha von Meyer.
Great. Well, thanks so much. It's a pleasure to be here. This section of the webinar is really aimed at students and people who may be expert in different technical areas without a traditional power engineering background. So what I like to do is give a little bit of context for different kinds of grid measurement data, and then see how PMU, or phasor measurement unit data, also known as synchrophasors, fit into that context, and develop a little bit of a physical intuition about what those data mean, and how we can start to sort of feel what they tell us about the way power flows in the electric grid. So for some of you, this may be very basic, but we want to make sure that, you know, we cover those fundamentals. Sometimes there's still, you know, it's hard to build an intuition around this. So sometimes even more experienced students have questions that hopefully we can discuss. And it's really great to be sharing this morning with Kevin Jones, who has a lot of experience working with PMU data in the real world. So between the two of us, hopefully we can answer your questions. So just as a really high-level overview, you know, there are different kinds of sensors throughout the electric grid at different levels, with different kinds of resolution. It's interesting to think about the fact that most of the legacy electric grid as we know it has really been around for over a century. So it had to be designed to work without a whole lot of measurement or communication, right? Electric grids could be operated in the days before there was even telephone lines between different power plants that were coordinating. So it's really quite phenomenal that the lights stay on even without detailed monitoring and sort of high resolution observation and control of different aspects of grid components. But of course, as things get larger, more complicated, and we have higher expectations on performance, and also we now have more interesting renewable intermittent resources contributing to the mix, there really is a need to understand things in greater detail. So there has been this trend toward higher resolution in time and space for measurement. You know, for many, many decades, there were just measurements at power plants and at the customers. And then in the sort of late 20th century, there was a proliferation of SCADA instrumentation at distribution substations and then out on distribution circuits. Transmission substations had been instrumented, you know, a little bit earlier, but it was not really dense measurement, not really rich measurement. It was sort of a really rough sense of voltages and currents to get the big picture of power flows. As we find ourselves operating the grid sort of closer to its limits, and we try to be more efficient and economical, and also we want to manage resources with higher resolution, we need more refined data, right? And so in the spectrum of different types of sensors, the phasor measurement units are a really important step because they actually show what we'll explain are the state variables of power flow in the grid. So they show us magnitudes as well as phase angles or very precise timing of voltages. And they also measure currents. Now, for context, I want to mention that, you can go farther in this direction with continuous point-on-wave data. So point-on-wave data tell the entire AC waveform in much greater detail, whereas the PMUs are really an abstraction that we'll describe. I really recommend this report on the NASPE website by Alison Silverstein and Jim Follum that talks about these different kinds of measurement data, and particularly point-on-wave data. Just sort of for a visual here to put this on a scale of different orders of magnitude in time, what we're looking at here are we're focusing mainly on the time frame sort of around a cycle, right? 1/60th or 1/50th of a second. And there's very different questions that you can ask about what's happening in the electric grid, and very different options for control or decision making that you can exercise at different timescales. And generally, we talk about steady state power flows at these longer time scales where traditional monitoring is often plenty. So SCADA instrumentation reporting every few seconds can give you a good enough sense of, how is the load, for example, relative to the capacity of the system? Are you not going to overheat something? But then if you're looking more at the dynamical response and see how things change, and also see what happens when things aren't exactly like in the textbook, when you have disturbances that are, causing things perhaps to oscillate, or when you have faults, those are the situations where you really need to zoom in closer. So for point-on-wave data, traditionally there have been digital fault recorders that record the entire AC waveform, but just for a short period of time and locally, to understand the fault locally, to make a decision, for example, about whether to open a circuit breaker. But that information hasn't been historically correlated with other locations, right? So when we talk about grid intelligence, really an important piece is the correlation between different places. And so I want to give you an example just with these micro PMU data of the benefit of even just having voltage magnitude data that's reported many times per second, as opposed to once every 5 seconds, to sort of appreciate the texture that you get to see. So in this picture, we have 2 micro PMUs at different locations in the San Francisco Bay Area. The blue one is in Berkeley, the red one is in Alameda. They are separated by a 115 kV transmission network. But you can see here that there's a fault event, and for each location, I should say, there are 3 phases, ABC phases. So there's some fault event somewhere in the area, and both of these PMUs are picking up the voltage sag that came with that fault. So one important point here is that high impedance faults, which are dangerous, they are faults that can be caused by any number of things making contact with electric conductors that they're not supposed to, whether it's tree branches, animals, and what have you. They don't draw enough current to trip a circuit breaker or blow a fuse, but they can start fires, which we're now very keenly aware of. And being able to recognize where that's happening can point you to a faulty piece of equipment or a tree that the tree trimming crew missed, to be able to take care of that situation before it starts a fire. So you can see here in this time series stream that with 120 reports per second, you can get a very detailed profile of how the voltage dipped down on the 3 different phases and then recovered. And without these PMU data, you might not know that anything happened, right? This could have been a tree branch or an animal somewhere. No one would be the wiser. Identifying that high impedance faults are there, diagnosing why solar inverters tripped offline is another application here. Or you can see that there's this pattern of how the 3 phases relate to each other, and you can actually use these correlations to line up what's phase A, B, and C. And Mohini will talk about that in next week's part of the webinar. You can determine connectivity of the system as well. So there's a lot you can do just with high resolution magnitude measurements before we even get into phasers. But so what are synchrophasers? What's this phaser representation about? I'm using an analogy here of a photo of me and a stipple portrait that's an abstraction. It's a simplification. It's a way to get sort of a general character across of the thing you're representing with less data, right? It's easy to print this stipple portrait with a small amount of black ink. It doesn't show you everything, doesn't show you skin color. We make assumptions about what variables are held fixed. When we simplify and abstract, it's really a lossy compression of information. So you can't tell if, I'm red in the face in this picture. If a person were illuminated with different color light and then you try to do the stipple, you would get maybe an unrecognizable picture. So with electric waveforms, we can abstract them into phasers on the assumption that there's a kind of behavior that we all agree is there. Namely, we assume that there's a sinusoidal waveform, which we can then represent in terms of just 2 quantities. And those 2 quantities are the root mean square magnitude and the relative timing of the sine wave compared to a reference clock or compared to another sine wave. So graphically, if you're not a big fan of math, this picture is kind of all you need to translate the height of a sine wave. And here I've actually shown the full amplitude rather than the root mean square that we use by convention in engineering. But either way, it's a measure of the height of the curve in green, and then a measure of the timing relative to when somebody pressed the stopwatch and said, this is time equal to 0. And that's in red, and that time dimension becomes an angle. And so in the complex plane, where the imaginary number is the square root of -1, it's the thing that can't decide if it wants to be positive or negative, so it just wiggles. In that plane, we imagine the phaser is rotating, which is a representation of this sinusoidal sine or cosine waveform. So if you're not into the math, you may avert your gaze for the next slide. Just for those of you who are reviewing or are studying power engineering, the way you get to this notation is you basically imagine that the sine wave is a projection of a helix, of not just a sine wave in one dimension, but a 2-dimensional sine wave, just like a corkscrew, right? So if you take your wine bottle opener and you look at that corkscrew, any direction that you look at it will look like a sine wave. So you're writing the voltage, could also be the current, as a function of time rather than just a cosine. You say, well, let's suppose that cosine is just the real part of a complex expression, which includes the cosine and an imaginary sine of the frequency omega times time plus the phase shift Greek letter phi. J is the root of -1. So we haven't changed anything. We've just said, well, the cosine is just the real part of this expression cosine plus J sine. Then we can use Euler's equation to say, well, that's equivalent to a complex exponential. And that complex exponential is implicit then in the phasor notation that we use. It has a rotating part, which is the e to the j omega t, and e is the base of the natural logarithm. And if you're not familiar with Euler's equation, you need to be, because it's the coolest equation there is. So the e to the j omega t is a part that rotates around in a circle, and the e to the j phi is the part that tells us about the relative phase. So the e to the j phi is the metric that really places the phasor in the complex plane. What this amounts to is you taking your wine bottle opener, you're taking your corkscrew, and now you're going to turn it around and look at it from the end so that what you're seeing is a circle, right? So we're going to eliminate the time dimension. We're going to ignore the e to the j omega t, because we'll say, well, everybody knows what the frequency is. It's just 60 hertz or 50 hertz. So we won't talk about that. And then we have just the magnitude and this exponential e to the j phi, which we write in a shorthand with an angle symbol. So we've basically said there's two pieces of information to know. Everyone already knows the frequency, so it's that time shift and the magnitude. We'll come back later to what happens if we didn't know the frequency. But so the snapshot in time, so on the left now we're looking at the corkscrew from the end, allows us to very conveniently compare different sinusoidal waveforms. So the gray one is 90 degrees ahead of the black one, and we have this implicit rotation in the counterclockwise sense that says, yep, the gray one is 90 degrees in front, and it's a little shorter than the black one. So that's a way graphically to very easily represent the relationship of different sine waves. And, you know, power engineering textbooks are full of phasors because it's so much more of a concise representation. Now, a short digression, we have three phases in our standard AC system. And at the transmission level, typically it's a pretty good assumption that those three are balanced. So you could measure just one of the three, or you can give what's known as a positive sequence representation, which is basically a kind of average of the three phases. And a lot of the transmission level PMUs do that rather than reporting back all three ABC phases. So if you're not familiar with that term, the positive sequence just means it's the part of the three, a component of the three that has kind of the right ABC sequence and represents them as all being the same magnitude and exactly 120 degrees apart. If you look at distribution systems, you will find that they can be really unbalanced. And then sometimes it's necessary to look at all three phases explicitly, or to think about the three different mathematical components that are positive, negative, and zero sequence. So that's another fun adventure. But coming back just to the, simple single phase representation, let's think about the time dimension here. So the AC frequency is never exactly constant, right? So when we are looking at the phase angle of one particular sinusoid relative to when we decided to press the stopwatch and say this is time t equal to 0, we will find that, well, that relative angle is going to be decreasing or increasing depending on whether the frequency is greater than or less than 60. So what that means is when we look at a time series picture of phasors, we see this like characteristic, sawtooth kind of pattern, where in the first part of this upper graph, we have the phase angle increasing, not at an exactly constant rate, but, so this has the frequency being slightly greater than 60. And then at some point right in the middle, the line is flat, and when those degrees of phase angle stay constant, that means the frequency is exactly 60 hertz. And so the math that calculates the phase angle reports a constant number. And then the frequency in this system drops down a tiny bit below 60, and so that's when the degrees go down. So one of the things that you have to do when you're using PMU data, first of all, is to unwrap what is going to go up or down to 360 degrees and come back around at 0, right? Really, you don't get physical meaning from a single phase angle report from a single PMU, because it tells you what the frequency is, but it doesn't tell you anything about power flow. To understand how it kind of physically reports what's happening in the grid, you need to compare it to a PMU measurement from somewhere else. So in the lower picture, there's 2 different PMUs, and we're comparing the voltage phase angle between the 2 of them. And you can see one is a few degrees, the blue one is a few degrees ahead of the red one. So that corresponds to a meaningful steady state power flow between those 2 places. To do that, you need to use the same clock, right? You need to compare your measurement of the waveform to the same time reference. And it was GPS satellites that made that economical, short of every PMU having a super fancy atomic clock built in. And, chip scale atomic clocks, I should say, are actually getting cheaper and are becoming a feasible alternative to GPS timestamping that security experts are, thinking about, because GPS is not completely invulnerable. But it was the proliferation of GPS data and having GPS receivers that are affordable, that could be built into PMUs, that made it possible to actually have a geographically spread out network of PMUs that are relating the voltages and currents, but in particular the voltage angle between different locations. So the clock has to be pretty good. And this is depiction of the time precision criteria for a micro PMU, which we developed at Berkeley with Power Standards Lab under an RPE project starting in 2013 to see just how precise could we make a PMU measurement in terms of having the exact alignment of the clock between different devices. So that timescale gives you a little sense here of where a degree of phase angle separation sort of fits in. To distinguish power flows on the distribution system, really you want to get down to 1/10 of a degree, which is about 4.5 microseconds. So your clock accuracy and your timestamp has to be better than that in order to meaningfully resolve this. The analog samples in the micro PMU are at 512 per cycle. So that comes to about 30 kilohertz or so. These vary a little bit across PMUs, but you really have, when you talk about samples, you have to be very careful whether you're talking about analog samples of the waveform, like in a real photo, right? Or whether you're talking about the data frames that are reported, which are like the dots that are reported. And these are, depending on the PMU, somewhere between once every other cycle to twice per cycle. And so hopefully that's a useful reference for you. Speaking of precision, and I think precision is a better term than accuracy, because there's many things we don't know. For instance, oftentimes PMUs make measurements through voltage or current transformers. And those instrument transformers are not exactly accurate, right? So the quality of the measurement, the accuracy of the measurement is only as good as the transducer or the weakest link in the chain, but the precision just refers to the ability to resolve differences. And there's a standard referred to as a total vector error that's been used in the industry that says, well, basically you should be within plus or minus 1% of the magnitude of that vector in the complex plane. Now, it's interesting when you draw this circle of 1% magnitude around the tip of the arrow and say, you know, your measurement should land somewhere in the circle of the true value. That has two different dimensions, right? It has a time dimension, sort of in the azimuthal direction, and a voltage or current dimension in the radial direction. And if we zoom in on that, say, well, what does 1% total vector error tell us about the time resolution here, or the angular resolution? We get that it's basically about a half a degree of angle. So one conclusion is that the 1% total vector error, which is perfectly fine for looking at power flows in large areas, doesn't really tell you enough about steady state power flows on distribution systems. I want to kind of shift gears a little bit and talk about the physical intuition for what these phasers tell us. This may be old hat for many of you, but it's important, I think, to sort of have a visual of how different components in the electric grid stay locked in synchronicity. And so what is synchronous here? Well, it's rotating machines that are synchronous. And the analogy in this picture is from, you know, an old-fashioned factory where different machines are linked, just analog mechanically, by this belt that's connected to a common shaft. And so we have a shaft running along the ceiling that is a way to distribute power, because you could have a motor that is driving the shaft, and then you can have the shaft driving other motors. The belt can be pulling in either direction, and it could be either taking energy out of the common shaft or putting energy in to that rotation. So since everyone has that reference, that is the system frequency, right? It's the rotation of that common shaft. And in the electric grid, there's an electromagnetic set of forces that take the place of just the belt and friction and mechanical pulling. But this makes it very intuitive that you can, if the balance of power generation and demand is off, then the whole thing is going to speed up or slow down, right? Which is what we observe with the system frequency. But more so, thinking about how we conceptualize this phase angle, is that the shaft really has a little bit of a twist in it. And, you know, if it's steel, it's going to be quite rigid and not twist very much. But if it were a rubber shaft, you could really visualize how it could be twisted. And in the place where you're driving it forward, it's going to have a little bit more of a forward angle twist. And in the place where the shaft is pulling a heavy motor, it's going to be held back a little bit. So that is, I think, a nice mechanical analogy to the voltage phase angle, which is going to be twisted as you transmit power across a transmission line, which is now our analog for this common power reference or resource. And in fact, if you measure exactly the timing of your voltage phase angle at one end and the other end of a transmission line, you find that they have to be, by the laws of physics, shifted or twisted a little bit by what could be a fraction of a degree or quite a few degrees, depending on how far you're going and how much power is flowing. So this is from FNet, which is a great resource for sort of wide area visualization. from UTK, University of Tennessee at Knoxville. And it gives you a visual of a gradient, like a heat map of a voltage phase angle, and they show you this online in real time, of where power is flowing from one place to another. So this should be kind of a visual reference of the places where more power is being produced. That's where the phase angle is more forward. Now, again, if you're not into the math, you can avert your gaze. But for many of you, this will be a good review or an interesting maybe prompt to read more about the actual power flow equations in a large network. And what's really cool is that for any location, any node I in a network, you can write the real and the reactive power, P and Q. So the reactive power is power that's circulating because of inductances and capacitances in the system. That's not doing useful work, but that's essentially sloshing around because the physics demands it. And we need to account for both real and reactive power, and those can be written as functions of the voltage magnitudes and phase angles at every node I in the system relative to every other node K. So the voltage magnitudes and phase angles are the state variables that determine power flows everywhere. If I give you the voltage phasors at every node in the system, the state is completely described unambiguously. On the other hand, if we have the real world problem of knowing where power is injected and demanded, if we then want to solve for what are the voltages, the magnitudes and angles, that actually is a very tricky problem, which we have to do numerically. There's not a closed form solution, and there could be more than one mathematical solution. So power flow analysis is a really interesting field. It's all based on the voltage phasors being that variable that drives the power flow. So for real power flow between two locations, a really useful approximation, great rule of thumb, is that it goes as the product of the two voltage magnitudes at the two locations divided by the inductive reactance X in between. And that's, we're assuming, is pretty much describing the impedance of the transmission lines in between. We're assuming here that transmission lines don't have much resistance, which is a good assumption because they tend to be pretty hefty chunks of, aluminum and steel. They're made to not be too lossy, but they have magnetic fields around them, which makes them inductive. So that property dominates, that property X. So that's the constant V1, V2 over X, and then times the sine of the angle difference between the two locations, delta 1, 2. That's delta 1, 2 is the difference between the voltage phase angle at location 1 and at location 2. So that gives you a power transfer that looks like this sine function. And you can already see that it has a maximum at an angle separation of 90 degrees. If you get anywhere near there or fall over the edge, the lights go out. It's a very bad day. And really, for purposes of keeping the grid stable, you want to maintain phase angle separations in the tens of degrees, somewhere here in this nice, safe, linear range of the curve. And there's a whole field of analysis of figuring out, well, exactly how far can you drive this, because the relationships between synchronous generators at either end gets a little weaker. And we'll come to that. I just want to give you a visual of how the phase angle difference relates to power flow. And this is from a distribution circuit. So we have very small phase angle differences here, something like a degree or a degree and a half. But you can see how that correlates with the solar power that's produced at one end of this distribution feeder. Here's a picture of two generator units to try and get a little bit of that intuition about If the voltage phase angle is more forward, that means the generator is pushing harder. It's facing a stronger reaction. There's physics that is making it push against a stronger magnetic field. And that's a visualization of how we're driving power flow from one power plant to another. So it's where the voltage angle is more positive that we're injecting more power. I'm not going to spend too much time here on the physics of generators, but the point is that there's a feedback system or a feedback mechanism between how far forward the voltage phase angle is and how hard the machine is pushing. So that is what keeps everyone in lockstep. And if we disturb the system, we're going to see an oscillation that's sort of this classic damped harmonic oscillation, which comes out of the swing equation that physics students recognize as, a classic dynamic system, a second order differential equation. We're relating the rate of change and the second rate of change, or the acceleration of that voltage phase angle delta. We're relating that to the difference in mechanical power input and the electrical power that's injected into the grid. So this is really the reason that it's been possible to operate electric grids at all. But it was never directly observable until we had PMUs, right? Because you couldn't actually watch the instantaneous position of a generator rotor. So now just a few more pictures of data. This is just a transmission line trip event in the Western system that shows you, PMU reporting a big drop in frequency. And we can see that kind of classic oscillation. So these are types of events for which PMUs have been super valuable, because this is not something that was recognizable in detail if you didn't have data that were much faster than 1 second. You can see the time scale on this graph is, the units are in seconds. And you see generators tripping offline and a transmission line tripping, and then other generators responding. Here's an illustration of a big event of frequency oscillations after a large chunk of generation went offline. And what we're seeing, what's really interesting, is that even though the generator was lost in Southern California, some of the biggest swings are up in Canada. So that illustrates how much physically the whole network is connected. And it's wobbly in part because there's such a big phase angle difference between the two ends, with a lot of power flowing from north to south, that you're seeing these big oscillations. And Kevin can say a lot more about this. We didn't even know that our Western grid had these standard modes of oscillation until we could observe them with PMUs. And this really is what sets the limits for power transmission, more so than the thermal limits. So just quickly wrapping up, what happens if our signal is not a cosine? And I want to thank Harold Kirkham for some of his papers on the subject, and really raising awareness of the fact that, we're all cheerfully making this assumption we're describing a cosine. In the type of event that I just showed you, voltage as a function of time is not exactly a cosine, because frequency is changing, right? So what is a PMU to report? It's not unambiguous. What should be the right answer? If we talked about phase angle differences between two sine waves. If, like on the right, those sine waves don't have the same exact frequency, then what do you report as a phase angle difference? You can compute a phase angle shift between these two sine waves at some place, at some section, at some point in time that you choose, but it won't be universally true for all past and future times, which is implied in a cosine that it's that way for all past and future times. So the sampling window actually becomes important, and which chunk of time are you actually referring to? Here's another good one. What if you have a deformity in this cosine waveform? There's not strictly a magnitude and phase angle shift that would be the correct answer for a PMU to report. So people in the industry are talking about what rules should we agree on for describing this kind of situation. Or is there a way perhaps to capture a goodness of fit measure, as Harold Kirkham has proposed, that sort of gives you a quantitative metric of, well, how is our waveform conforming to the assumption that it was a cosine? Like in the top row here, we have just a plain cosine function. If we allow for the fact that frequency and phase are actually drifting in time, then there's a way to account for all those terms, but we have to agree on what we mean by the frequency here. Is it just the omega? Is it the rate of, which rates of change do we include, and how do we report the rate of change of frequency, which is an important measure for a sort of understanding how dramatic a disturbance event is happening. How exactly are we to define and quantify that? So we do live in interesting times. This is one of my favorite graphs. This is from an event where there was a major transmission line trip, a couple of trip events, and then solar inverters were reading the frequency of the system, and they were reading something like 57 hertz, which is not what others computed, but there's different algorithms for computing frequency. And so the solar inverters did what they were told to do, which is to disconnect. But that led to 1,200 megawatts of solar resource suddenly disconnecting, which was not the intended outcome. So in particular, with variable resources and inverter-based resources, which we have the luxury to program exactly how we want them to behave, there's a whole different field of opportunity to sort of tune them to the needs of the grid that we're understanding with these very precise measurements. So with that, I think I will close and turn it over to Kevin.
I guess that's my cue to jump in and get started. Let me just take note of the time here. Okay, so 12:55. So we're going to jump from school to work, and I'm going to do my best to make that transition as gentle as possible. But my talk today is going to be centered around application of this kind of data for solving problems in the electric utility. And it's going to draw from the work that's happened at Dominion Energy over really more than a decade at this point, with a focus on the last couple of years of work as we've become more competent in our use of data at scale. So I'm going to try to reframe this. I've presented this content before in other venues, and I'm going to try to reframe it in two ways. One is, what are the lessons learned for folks that are moving in the direction that my team has moved in? What are the things that they need to keep in mind as they progress, and what are potentially some of the things that they should avoid? How should they think about these things strategically and organizationally? And then the second is some really interesting case studies where we've been able to exploit our synchrophaser data and data analytics platform to do some really interesting things. So with that, I'll jump in. I alluded to the fact that we've had a very long history in synchrophasers, we as in Dominion Energy, but also me personally. The story begins for Dominion and me in the exact same year. My very first semester of grad school, I was indoctrinated into the world of synchrophasers back at Virginia Tech, and have really watched it evolve both at the community level and at Dominion over that time period. And I'm going to make an assumption that there are some young folks or, well, I guess I'm technically still young-ish, but some younger folks on the call. And I know that we live in a world of constantly changing job titles. We move from one role to another, and I would challenge you to find something that you can do, even if it's across multiple jobs, but something that you can be a part of for 10 years. Looking back at a decade of your life and seeing that kind of transformation is really special. So I would really encourage you all to do the same. But in terms of Dominion, there's a few key points I'll make before we get into some of the details. One is the DOE was really, really helpful in catalyzing our work with synchrophasers at Dominion. The second thing is we've got a lot of PMUs. Now, it took us a while to get there, but we have nearly full transmission system coverage with synchrophaser measurements in many of those ways that those measurements are redundant, meaning we have the same measurement from multiple devices. And to put a number to it, we have approximately 40,000 individually measured physical quantities. That includes voltage phasers, current phasers, frequencies, digitals, all of those things. And as you can imagine, the path forward wasn't very linear. And we'll talk about that in a moment. But in the last few years, what we've really done is taken all of that data and really challenge ourselves to find a meaningful return on investment from that. So, but I'll start with a story from 2017. We did all these really great things, and we had all this data, and we'd made a lot of assumptions about how we were going to manage it and how we were going to use it that had really never been stress tested. And what ended up happening was that we found out very quickly that our enterprise data historian just wasn't up to the job of not only ingesting, not only visualizing and analyzing our synchrophaser data, but sometimes just ingesting it itself. And we put together a plan, and the plan was, for a number of reasons, just very silly and couldn't guarantee us at the end of the day that we would actually be able to do any real analysis on large volumes of historical data. And so this required us going back to the beginning, and really try to think about this problem from first principles up. So we realized very quickly that this problem of working with high resolution time series, which synchrophasers really are sort of the first class of data that falls into this category for the utilities. Certainly you have event waveform data, but they're so small in nature, even the density doesn't become a problem. But like continuous high resolution time series is a very special computer science problem. And even the best technologies that exist out in the world, made by some of the household names, the Googles and the Amazons, were not designed for this kind of problem either. And so at this time, I took it upon myself to really understand, well, why in the heck is this so hard? Why can't I work with the data the way that I want to work with the data? And it led me to find a startup company who, now I guess are based out of Washington, D.C., called Ping Things. They're the prime on the NI for AI project that we're here talking about today. And they're the ones that built the technology that we ultimately ended up using to find a home for our synchrophaser data. So all that being said, we needed the right tool for the job to be able to push our use of synchrophaser data forward. And the way that we sold this internally was with a very simple concept that basically our use of data was burdened by the cost of experimentation, and that if we wanted to be able to use data effectively, until we drop the cost of experimentation below a certain threshold, we won't use data at all. So it's very much like an activation function. There's a threshold at which until you meet it, nothing happens. And it's not that analysis would take 10 times longer if you had something 10 times as slow. It's that you will never be able to perform the necessary data analytics workflows until you have reached a sufficient cost performance threshold. So until you can drive down the cost of experimentation, nothing's going to happen. And there are a few contributing factors to that, right? A lot of people in the community believe that there's this idea of a killer app for synchrophasor data, and maybe there is. Hopefully I will be proved wrong, but I believe that this is a false god, because what I really perceive is an ensemble of applications that are driving the value proposition for synchrophasors at a utility. And feeding into that is how very different and niche each utility organization is. So there's not this cookie cutter approach that other sectors can take to get to have killer apps be as impactful as they are. And the other thing too is the industry is very nascent in its use of synchrophasor data for long-term historical analysis. And so no one really knew what we were going to use it for. There's a lot of a priori guesses, right? Here's what we think that it will use, but really we need to experiment. So it's this need to rapidly prototype and evaluate hypotheses drives this notion that if we don't drive down the cost of working with data, nothing's going to happen. Not only will we not work with the data, but we'll never figure out what it is that we're supposed to be doing, or what is the most valuable use case for that data. So I'll also highlight a few of my contrarian opinions that drove us over the last few years in terms of technology. And this is really speaking to the same technology that is under the NI for AI platform that you all will be able to play with and have access to. As I mentioned, it took a first principles approach to realize that this was the right solution. We also deviated from a lot of the contemporary data analytics solutions and went with a platformed approach instead of a siloed application. For example, if you look at something like Breaker Health Monitoring, there are apps out there that do just that, but that doesn't give us what we need. And the other thing, and I can't understate this enough, I can't overstate this enough, going with a cloud-based approach versus an on-prem approach was absolutely fundamental to our success with our collaborator Ping Things. So this is really important for any of the utility folks out there that are a little bit scared by that word. Don't be. For you personally, it will be career making. For your company, it will be a godsend. So don't be scared. The other notion here that I want to point out is the synchrophasor community is very focused on real-time operations use cases, as they should be. But I think we approach myopia to some degree, because the pace of innovation in the control room is, well, what it is. And at the end of the day, my job was to define a return on investment for synchrophasors, our synchrophasor program. So I had to pivot resources to engineering applications, basically business intelligence, things that happen on a slower scale. And this pivot was fundamental to us driving our value proposition forward. And then the last point that I'll make here is a lot of data analytics use cases have a value proposition that's centered around reducing O&M costs. And while that's great, I don't want to poo-poo on that. I actually believe, particularly for a company like Dominion, that if we can move a needle and one needle only, I'd rather move the capital needle. The capital needle is much, much bigger. And in terms of our ability to have a larger impact on the company, our financial performance, or society in general, particularly in a world of renewable integration, I'd rather focus on capital. And I'll touch on this later when we get into some of our case studies. I mentioned before that we'd worked with Ping Things to set us up with the right technology solution for our data analytics program. This is the same technology that's under the NI for AI platform that you all, so literally the exact same thing that Dominion is using is what the NI for AI community will have available to it. I'll point out really two things here that are really important for utility perspective. First is that working with Ping Things was basically a one-stop shop for all aspects of this transformation. IT played a minimal role, and because of that, second point is that we were able to go from signing a contract to streaming data and doing analysis in about 4 months. So the pace that we've been able to innovate at is really not a utility pace. It's been transformational for Dominion and for all of the individuals that have been involved in that work. Something else that you'll get a really nice taste of on the NF for AI platform is the interactive human scale data exploration. So I like to think of it as Google Maps for time series data. There's a very intuitive zooming and panning that is really great for analytics workflows. And it underscores a fundamental principle that you should be thinking of when you're working with data. And that is, you must look at your data. It is the first and the 50th and the 100th step in any analytics pipeline. And so the purpose of these tools is just to make sure that any data that you want to see is at your fingertips virtually instantly. This alone has driven some value propositions inside Dominion, particularly in our fault analysis group. And that's, I forgot that I had this slide here. I'm going to skip this. It's there for you guys to take home and read, but just know that the data visualization has accelerated our ability to do fault analysis to improve restoration times. The other aspect of the platform that's really powerful from a user perspective is the ability to write code to do your work, and to bring that code to the data rather than having to download the data to your workstation and do your work there, the sort of traditional MATLAB approach. So in terms of rapid prototyping and analytic exploration, this is just really, really powerful, both for the exploration of new use cases, as well as for more production quality applications as well. So for the exploitation of use cases. So regardless of whether you're a beginner, intermediate, or an advanced user, this is a really great way to work with data. All you need is a little bit of Python knowledge. And honestly, I believe that the platform has some other language plugins as well. I don't want to quote what's there, but I know it's more than Python. I'm a big fan, and that's what we use in our team. Speaking of, when I talk about fast growth, I can talk about it in terms of our team as well. In July of 2019, there was a team of one, essentially, just me. And over the last, well, what are we at now? Not quite 18 months, 15, 16, 17, we're in that time frame there. We grew from 1 to 2 to 3 to where now I have, come November, I'll have 6 full-time people on staff that are only working on these problems, in addition to 2 graduate internships that we bring in each summer. So we have folks that are working on data analytics, some folks that are working on the modeling tie-ins, which there are many, some folks working on data engineering and technology, but at the end of the day, we have some dedicated resources here, which is really exciting. We've also been very busy. So in terms of answering the question of, well, what are the most interesting use cases for synchrophaser data, at least for Dominion, we've got a laundry list in various levels of technology readiness. And I won't belabor going through these one by one, but I will point out 2 that are on the more mature side that I'm calling here as StatComm control design and dynamic performance characterization. And supporting both of those under the hood are really dynamic analyses of synchrophaser data. If we recall the original question before the presentation about, can we use these things for more than steady state? So we're looking at oscillations We're also looking at spectral analysis and mode and damping estimation. And as you'll see, we're not just looking at these in terms of discrete events on the system. We're looking at them in terms of the continuous and ambient data 24/7 across the system. Now, we aren't just synchrophasers. We also upload event files. Those are both transient events, but also longer-term waveform captures. So we'll do as many as 15 minutes continuous waveform. We have PMU data that extensively covers the network. We've talked about that. We can also ETL SCADA data over from our Pi system. And we're also uploading network model snapshots from our EMS system at a 10-minute interval. So we can do a lot of really cool things with that, and all that's going into predictive grid. And certainly there are some things that we can hope for in the future as well. But today, with the remaining time that I've got, I want to point out, I want to talk about one particular type of analysis in particular, because it's going to be useful for understanding the variety of case studies that we are that I'm going to share with you. And so this is basically our small signal analysis toolbox. And what it allows us to do is to take signals of voltage and current and frequency and angle and look at them over long periods of time, minutes, hours, days, weeks, months, across the system, and understand across the frequency spectrum that is visible, what are the modes of oscillation that exist, what are their energy levels, what are their damping. And so you can see here, bright areas represent modes of oscillation, brightness represents energy level, and then of course time is on the X and frequency is on the Y. And so we look at these things a lot, and I wanna point out again, like, we're not looking at events. This is ambient data that we're looking at, and there's a richness there that is, I don't want to use the word surprising. We always hypothesized that it was there, but it's really exciting. And being able to look at this kind of analysis at this scale is quintessential big data problem, and is something that we'd only be able to do with our collaboration with Ping Things. So let's jump in and talk case studies, and I'm going to go through these in a little bit of a rapid fire approach, because I also want to crescendo at the end of the talk with a few things that'll get you thinking. So first thing, and these have been scrubbed of specific locations, so I am purposely being a little bit generic, but the first thing is that there's a lot of activity in the frequency spectrum from industrial dynamics. And this is important because we need to recognize that the distribution circuit, not just from a load perspective, but from a generation perspective, is no longer a passive element in the system. And these behaviors need to be quantified because they can potentially interact with each other. So an industrial driven mode of oscillation might not cause a lot of problems in isolation, but imagine a world where you have ubiquitous solar or other inverter-based resources. This could become a problem, not just with the load dynamics, but with them interacting with themselves, which is a great tie-in to our next case study. We're also looking at oscillations from solar sites, both distribution connected and transmission connected solar sites. You can see here there's an 8 hertz mode in the second half of the day here. Now those vertical striations are actually an arc furnace that is close by that's just muddying up the frequency spectrum. That's not bad data. But we see a lot of activity from our solar plants. And this is important because, as I mentioned, as we increase the number of these assets on the system, the proclivity for interaction is profound, and our models are unable to predict it. So we want to do two things. We want to first use the data to improve our grid models so that we can do analyses, to second, support the interconnection process. So we do all of these other studies to facilitate new interconnections, but now we're going to need to look at the small signal behavior of the system at the point of interconnection as well. Getting into some larger assets, we've also seen a lot of interesting stuff coming from StatComms. So StatComms are flexible AC transmission system devices. They're really meant as compensation devices. And in a world of renewable energy, they are necessary to maintain a level of flexibility and reliability in the grid. So Dominion, or companies like Dominion, are investing a lot in these types of assets, and they aren't cheap. So it's our job to observe their performance and understand if they're working correctly. So in this case, we were able to observe some modes of oscillation that we identified as correlated with loading in the area. And so we realized that the absence of an adaptive gain controller from the StatComm controller caused this behavior. And we were actually able to validate this hypothesis in the field with an in vivo experiment. Basically, we did we made some changes to the StatComm controller in the field while it was still energized, and we're able to observe the results. And we're able to confirm that yes, we do need an adaptive gain controller, and we were able to get some insights into what that gain needed to be. While those are StatComms in isolation with each other, there are also StatComms that are nearby each other and can also interact. So here's an example of a pair of StatComms that are actually part of a group of 4. This analysis just happened to include the 2 StatComms. You can see that there are some substantially undamped modes of oscillation that are almost 180 degrees out of phase from one another. And the impact of this is actually pretty interesting in that so these 2 StatComms are fighting with each other, which can cause equipment degradation, but the potential to fight with each other can actually drive down the gains of StatComms to the point where they actually aren't regulating anymore. And in the times that you may need them, they might not be there for you. Now, I am not an expert in StatComm, so I'm quoting some of our SMEs there. So if you have questions about that, I'll have to direct you to them. But the idea here is that these are not nuisance behaviors. These are behaviors that have to be identified and have to be dealt with. Same thing with our SVCs. For those of you that don't know, SVC is sort of a cousin of the StatComm, but it serves largely the same purpose. We've also been looking at those. Same concepts apply here as well. Now, we've been talking a lot about power electronics because of inverter-based resources and StatComms and SVCs, but there's a lot of other valuable assets on the system that we can look at from this perspective as well. In particular, our spinning metal, our existing generators. And so we've looked, in this case, at our hydro plant and, one of our hydro plants, and we're able to observe a fairly constant 2 Hertz mode of oscillation that was present whenever the unit was in operation. And what's really interesting about this example is that it wasn't present in any simulation that we run. So what we were able to do was to take the model and perturb it in certain ways so that we could figure out which component of the model needed to be modified in order to have this reflected in simulation. And in doing so, you achieve 2 things. One is you improve the model, but 2, you can also use this approach in a diagnostic fashion, because figuring out which component of the model is going to produce that behavior will tell you which component of the actual generating unit needs to be modified to eliminate it. So there's this really fantastic marriage of data and models for diagnostic analysis, and we're really just scratching the surface with it. I also alluded to the arc furnace in one of our earlier examples, and I'm bringing it up here really as more of a data wrangling example as opposed to anything else. just knowing that there's lots of other things that are going on out in the system that show up in your data that are potentially going to mask the behaviors that you're interested in. And there are techniques that you can use to eliminate these and still perform the analyses that you want. So just a very, very power systems, signal processing specific example of data wrangling for those data scientist folks out there. Oh, and I should say, for those of you that don't know what an arc furnace is, basically it's a place that recycles old metal, old scrap metal. And the way they do that is by putting all of the metal into a giant furnace and basically applying a three-phase bolted fault to it until it heats up so much that it melts. It's pretty radical. So check that out on the internet if you're interested. And our last case study here is about our nuclear gen and our gas gen. Similarly, we were looking at the dynamics there, and we observed behaviors that really we could only attribute to aliasing. And we ultimately realized that there was some subsynchronous resonance and shaft dynamics, and that's basically two contributing factors to it. One is a change in grid conditions that happens on a periodic basis, and also a change in set point at the plant. And we were only able to diagnose this because we turned to our higher resolution data. So we spotted something in our synchrophaser data, but it wasn't sufficient for analysis. And so we went to our DFRs and we set up timers so that we could capture minutes of waveform data, not from an event, but just from ambient conditions. And then we were able to analyze those and confirm some of our hypotheses. So again, just Sasha spoke to the need for higher resolution data for some aspects of analysis. And this is just a great example of that. So there's a lot of stuff there, and the pace that we're able to churn out these case studies is actually much faster than we're able to metabolize the results back into the organization. And I see that as a win, because previously our use of data was really encumbered. But now the thing that slows us down is really trying to take what we've learned and make the necessary changes, both inside of our organization and with our vendor partners that produce some of these assets that we're studying. Those time constants are not as fast as analysis, but that's just fine. What I'm hoping, though, is that you see that there is, even in just this one particular analytic methodology, a tremendous value in the use of synchrophasers, having the right analytics tools, and then building a team and investing in developing these competencies. So why does this matter? Particularly this analytic methodology that we're talking about today? Well, it really comes down to the elephant in the room, the one big transformation that everyone is trying to achieve in the current times and into the next few decades, and that's increased renewable penetration. And with increased renewable penetration comes the need for increased dynamic compensation devices, which are also challenged by a limitation of traditional solutions. So fewer wire solutions, more complex technological solutions, not just for cost, but for other drivers as well. And in that world, the likelihood that these devices are going to interact with each other on these parts of the frequency spectrum grows exponentially the more devices that you have on the system. So our job is to establish a baseline now and continue to quantify it as it changes over time, particularly as we interconnect each of these new assets. Because when you go to design new ones, or you go to place new ones, you'll need to take into consideration the small signal behavior at those particular sites. I think I missed a key point back here. So the other reason that data analytics, particularly with synchrophasers, is going to be so crucial as we move forward is that in a world where the burdens are much greater on the utility for justifying an investment, we may need to provide more evidence to support a particular solution, particularly when a solution might be tens of millions of dollars. So simulations may not be enough in the future. And we may have to use data and data analysis to help justify investments. This is something that isn't happening now, but I perceive could happen in the future. And in the short term, where in the business are things being impacted? Well, certainly we've spoken about the relationship between data and models. So anywhere where modeling is driving a business process, there's the chance for substantial improvements. The other thing, and we've alluded to this with our StatComm case study examples, that if we can observe the behavior of the system at a place where we're going to install a new asset, or we can observe an asset's performance, we can then influence, for example, the controller design of that asset based on real world data. And this notion also extends into the longer term planning world as well. And we didn't give you any specific examples of that today, but this is something that we're actively working on. We're anticipating a world where data-driven planning is really just as basic of a competency as using, say, PSSE to do N-1 contingency analyses. And the last thing I'll note is that our interconnection processes will need to be adapted to take into consideration not just flow violations and not just harmonics, but also small signal dynamics and behaviors in the areas where the interconnection is going to happen. So just another business process that's going to get changed. And to close us out, or to lead into closing us out, rather, I'm sharing all of this with you, and I've shared this with a number of other communities now, and really the cat is out of the bag, or Pandora's box has been opened, if I want to borrow the analogy that I use on the slide. Now that we know that these kinds of things are possible with data, it's only a matter of time before others start doing it. And once people see how significant it is for making better decisions with our investments and for improving the performance of our assets, then it won't be long after that until it becomes a requirement. So I see a lot of this as a new competitive advantage for utilities. I think it will help them tap into more affordable capital markets when played out at scale. And I think it's going to affect regulation. I think there'll be a point where your ability to analyze certain aspects of the grid with high resolution data is going to be mandated. And so it sort of leads into this idea of a new utility. And if we were going to describe what that new utility looks like, I think there are three characteristics that matter. The first is we're not just going to rely on physics. We're also not going to throw it away. In all the talk of machine learning and artificial intelligence, we don't want to forget about how much we already know about the way that our system works. So really, I perceive a unification of physics and data in some of the ways that we married them together for diagnostic purposes in some of our case studies. So it's not just power flows, it's also data flows that are going to matter. And at scale, I also think that we'll be able to be more capital efficient, both in the way that we build our teams and the way that we work, but also in terms of the way that we finance our investments. If we can use data to find a better solution than what we can through simulation, then we can repurpose some of the additional funds to help with things like faster renewable integration. And then really, and probably most importantly, in a world where, heck, we really don't know what the next 5 years are going to look like, which is very different than the past. How can we be more adaptable to the external changing landscape? And I think being able to analyze grid performance is going to be one of those. So now you are at a fork in the road. and I'm that older gentleman who's walking down the path there. And you're back here. This is a place where you haven't really decided what direction you or your organization is going to go in yet, or maybe it's more appropriate to use this analogy for your career as an individual. And so I'm hoping that some of the things that I've shared with you today make it clear that the path forward is very good for this type of data, for this type of analysis, for the technology that supports it, and you should move forward with confidence. I'll also give a few shameless plugs. The NASB conference, which both myself and several of my team members will be presenting at, is coming up in early November. Also, again, if you're interested in the NI for AI project, which is the topic of today's one of the topics of today's tutorial, the website is here. And if you have questions, this is my email address. Happy to take any of those. And one final shameless plug for today, and that is we have a really robust graduate student internship program. And so if there are any students on the call or any professors or any folks that know young people that are looking for the next step in their career, we're generally taking about 10 students across transmission and distribution per summer. And we just posted our internship postings last week. So they are up on the Dominion Careers website right now. And this is just a sampling of some of the universities that we've worked with over the last 10 years or so. So please, if that's something that you're interested in or know someone that is, please send them to the Dominion website. We'd be happy to see their application. So with that, I'm only 4 minutes behind. So Laurel, I'll turn it back over to you. Thanks.
Okay, I think everyone can hear me. Now, first of all, I'm going to be honest, I love giving this talk. It's a really fun talk. As you probably could not tell from my intro title screen, not a self-portrait, but it's just such a fun talk, and it serves as a great motivation for today's overall seminar and sort of a bigger picture. My goal is to sort of get us to think about what exactly is AI, and then really understand it beyond the definition and what the impacts are for, say, society, and then also more specifically, the electric grid and electric utilities. So we're going to start off by trying to answer this question. And if we go to the Oxford English Dictionary, well, this definition kind of sucks. Let's see, theory and development of computer systems able to perform tasks, blah, 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 requiring human intelligence, blah, blah, blah. So the problem here is that human intelligence is really not well defined. And every time computers do something that we thought only people could do, we don't call it AI anymore. We actually just call it, we give it a different name and keep going. So the definition changes over time. And we can actually see that by just looking at the news. Here, AI from Microsoft and Google actually outperforms humans at picking out objects and images. That's crazy, right? This is a human skill, but apparently not so much anymore. And this is from 2015, the beginning of 2015. So computers have gotten better in 5 years. Now, here's another example, again, this one's from mid-2015, where computers taking an IQ test actually do just about as good as the average graduate student, like master's level. So if you only have an undergrad, the computer can probably do the IQ test better than you can, which is also nuts. This is, human level intelligence. And then I love, let's see if it's going to show up or not. Of course, it might not. Okay, so this is a video that demonstrates a Q-learning routine that's learning how to play the original Atari game Pong or Breakout. This is where you have a row of bricks at the top, and the computer is watching the screen. The computer is controlling the little joystick, and the computer is learning very rapidly how to best play this game. You know what, there we go. Okay, let's see. Are you still seeing my PowerPoint?
Yes, we are.
Kind of hold out a little bit. Probably increase, but I think now would be a good time to start.
Okay.
Okay, so apparently I'm not going to be able to show you the video, unfortunately, but what I will say is that the computer basically learns to become an expert level much better than human performance in about 4 hours of training. And again, this was from like a couple years ago. So here's a machine learning how to play a video game far superior to a human and far more quickly. So if we then go to a panel of experts, say a room full of data scientists, obviously not pictured in the photo, and we asked what AI is, we would get 100 different answers, right? There's not a good consensus definition. So to define this term, we need to go to a different group of people with too many degrees. And we can ask economists, and when we do, they would say that AI is a fundamental technological advancement, much like fire or the wheel or the steam engine. It is a fundamental technological advancement. And so the next obvious question, well, what does that mean? How does that help? So what we're going to do is we're going to look at one of the more recent fundamental technological advancements, basically the development of the computer. Obviously, this is Alan Turing, well, Benedict Cumberbatch playing Alan Turing in The Imitation Game, looking at Bletchley Park in World War II with a very large electronic computational device that was used to crack the Enigma codes through brute force calculations. What we're going to do is we're going to look at how this technological advancement, what happened, what were the results. And really, when you think about it, the computer, the CPU in your smartphone or your laptop, it allows us to do calculations where before the calculations were very expensive because doing them by hand was hard. Now we can do them very cheaply. So that old, if you flip to the back of the old textbook and you see that table of trigonometric values where, you look at what's the cosine of 3 degrees, because it was expensive to compute that back in the day, you had a table. Now you have a calculator or an app because calculations are basically free because of computers. But as the cost of calculations fell, really weird things happened as a result. Here's the F-117A, the stealth fighter, the wobbly goblin, as nicknamed by its pilots, in the upper left. And obviously the distinctive thing about this plane is its faceted surface. And it's designed to deflect radar, scatter it in all sorts of different directions, and minimize its radar signature. So when they originally designed this plane, they did not have the computational power needed to test out and simulate curved surfaces. Too many computations. So it's faceted. Fast forward the clock, and the B-2 stealth bomber, pictured below, was developed about a decade later, give or take, and we had much more computer power available, so guess what? The surfaces are curved, and they reflect and minimize the radar signature far better, much bigger plane. So then, as we get used to having cheap calculations, what we do is we take problems that were traditionally cast under an original set of assumptions, and we recast them as calculations. And I think photography is a great example where before they were like, photography was all about a chemical reaction to light and a development process. Now it's matrix algebra. And the technology on smartphones is such that with tons and tons of free calculations available, we're getting into computational photography where even having a very small lens with math you can compensate for, which is amazing. So then getting back to the question of artificial intelligence and what exactly is it? Well, it's a technological advancement, but what does it make cheaper? The answer to that is that AI makes abundant and inexpensive the capability of prediction. So in other words, the ability to take information you have and generate information you didn't previously have. Now, when I say prediction, there are unfortunately connotations associated with that. Most of the time, people think about prediction as forecasting, right? I'm going to use data from the day and yesterday and the week before to make a guess about tomorrow. Well, that is one type of prediction. However, there's another type of prediction where you are faced with an ambiguous decision based on the data available. And you predict which of the ambiguous cases is indeed appropriate given the available data. This is another form of prediction. And then, of course, especially relevant to many utilities, is the issue of missing data, where we're not talking about forecasting into the future. We're looking at historical data, but we realize that some of the data is missing and we want to fill in the blanks. This is another type of prediction. And if you're so inclined, I highly recommend a book called On Intelligence by Jeff Hawkins. Jeff built Palm Pilot back in the day, and he believes after he sold a bunch of companies, he spent his life trying to untangle how the brain works. And he believes that the core neural engine or kernel in the brain is simply one of predicting what will come next in terms of sensory input, so that the entirety of human intelligence is just based on our ability to predict. And there's actually good anatomical evidence that he's onto something. Good book, recommended. So if as prediction gets cheaper and better and cheaper and better, we see three things. We see, well, any goods or services that are based on prediction will get better. This is the obvious stuff. These are the boring use cases that everyone sees coming. These are the first to get addressed. But then, as we get used to having prediction everywhere and cheaper, our set of assumptions about how the world works change, and we start taking problems and recasting them in terms of prediction problems. And that's where the fun really starts to happen. And then really, as the prediction gets better and better and better, possibilities that we can't see from our current perspective, our current position, become possible. So what I want to do now is I want to look at some examples that you may or may not be aware of. This is a great one. Google started rolling out a service where they will predict what your response might be to an email so that you can respond fast, more quickly. And this is great because my mom would always email me about the random wildlife in their backyard. And then, of course, you know, the very short, oh, so cute, wow, like those are probably pretty accurate for how I would respond. And again, this is predicting. Some text comes in and predicting my response. Now you look at all of the hubbub about self-driving cars and automated driving or autonomous driving. And really the big leap that happened was when they abandoned this idea of trying to tell the car exactly what to do in all possible situations. Because they realized that, well, that works for autonomous vehicles in a constrained environment, like a factory, where a robot might be following a yellow line. It doesn't work on a real road surrounded by all these insane human drivers and all of these ridiculous road conditions that will present basically an infinite number of states that the algorithm will have to have prior knowledge of. So what they did is they said, what we're going to do is we're going to collect a bunch of sensor data, much as a human would perceive the road and driving in general. And we're going to cast the problem, recast it as one of predicting what a human would do given this input. And that's kind of the general idea for how they were able to make some pretty fantastic strides in self-driving cars. Now, this is my favorite because I'm guessing everyone here uses Amazon, unless you're fighting the power and Jeff Bezos and protesting or something. But I do, and I've been a Prime customer for too long. And Amazon has, they're pretty good at using data. So we're going to take a quick look at how they do this. Now, immediately off the bat, they are giving me a nice historical data display. This is not prediction, right? This is just basically giving me my data back. Here's your old orders. Here's how long you've been a customer, i.e. we've been tracking your life for now a decade. And then they're providing me some real-time data use cases, right? Hey, do you want to continue to watch Eureka? Yes, I did watch that show. And you looked at this book, or maybe you want to buy it. So reacting and potentially predicting actions that I may want to continue. But really, the interesting part becomes when you get to the predictive use cases, right? Where, hey, based on who we think you are and what you've done in the past, we believe you will want to watch Deadpool 2. And shockingly enough, they were accurate. I enjoyed that movie. I had not seen it at that point, so their prediction was accurate. And this is great because I'm sure predicting what I might need is a great way to increase your bottom line. However, you can it's kind of obvious. Like we can see that outcome from here. So let's ask a different question. What happens if Amazon gets so good at predicting what I'm going to want that they are 98% accurate? 98 times out of 100, they predict what I want, and they're right. What do you think happens? Well, at that point, at that level of accuracy, they probably just start shipping me stuff I haven't even ordered yet. And then I get this magical box that would show up at my house with a need that I didn't realize I have. And I would probably keep it and they would swipe my card. If Amazon can get to that level of predictive accuracy, then all of a sudden, instead of being a storefront, they're really just a shipping company because they already know what I need before I know I need it and before I know to ask. That's kind of amazing. And that would radically change their business model. I don't know if that type of store exists yet, but when it happens, and it will, because the predictive accuracy will eventually get good enough, what will commerce look like? Right? We can't see all of those implications from here, but we know that once the fundamental assumption that I can't predict people's future changes, then we don't know what's going to happen. So a pragmatic definition of AI is that it's the cost-effective use of data at scale. We need lots of data usually to solve prediction, or to use prediction to solve real-world problems. It's practical, it's easy to understand. It's a little bit better definition. So let's take a quick look and zoom in. Oh, this is an important point. It's cost-effective because whatever money I spend using that data, i.e. the data scientists, the big data platforms, the everything that has to, that cost must be exceeded by the return on that investment, right? I have to make money or businesses won't do it. So let's turn our focus to the utility sector, and let's say, take an example where we're collecting measurements, 3 measurements per meter every 15 minutes, i.e. this is like a smart meter. And we're doing this 24 hours per day. We're doing it every day of the year. And I got 10 million customers. At the end of a year, I would have collected about 1 trillion points or 1 terapoint. Now, if I just crank up the collection and every minute I'm collecting measurements instead of every 15, now we're up to about 15, 16 terapoints. And now let's go nuts and let's just collect data every second, every single second about or from these meters. And this yields a whopping 947 terapoints. So if we look at the cost associated with this, the total annual cost of storing data per customer at these different frequencies even collecting 3 measurements a second per customer, it's about 50 cents. And so really the question utilities must be asking themselves is, with second-by-second measurements coming from a residential customer's house, can I derive, or can I create, can I have some value-added service that creates more than 50 cents of value? And if the answer to that question is yes, so well, then why aren't you? Why aren't we exploring all of these use cases as aggressively as possible? Because we know Google and Facebook and Instagram and Apple would be doing this. So I want to finish up by asking an abstract question and trying to get you to see how this could potentially be applied to, say, the electric grid and the utility space, and to try to get a shift in perspective, if you will. So I'm going to ask, well, what is the area of a circle, right? And here's a PowerPoint perfect circle. And well, I'm going to tell you, I have the formula. It's a deterministic function. I have a physics-based model, if you will, of the area of a circle. And here it is. It gives me the answer every time. But because this is a talk about AI, and AI is really driven from data, from sensor data, why don't we try to do this in a data-driven approach? So what we're going to do is we're going to do the following. We're going to draw a square such that the circle inscribes the square, i.e. it's touching. It's tangential to the square at all the midpoints of the sides of the square. And what we're going to do is we're going to drop points. We're going to, in a uniform distribution, we're going to draw an X value and a Y value. And then we're going to drop that point in that square. And we're going to record a 1 if it's in the circle, and a 0 if it's not in the circle but still in the square. And then to compute the area of a circle, we're going to take the area as a percentage of the points that fall within the circle. It's a Monte Carlo. And so when we drop 1,000 points in this box and we use that to compute the area of the circle, we see actually it's a pretty reasonable estimate. The error is not terrible, but as we increase the number of points, then our error starts to drop precipitously. And we're getting 100,000 points. We actually have a really nice data-driven approximation of the area of a circle, an approximation of a deterministic function, an approximation of a quote-unquote physics-based model. So really, if we go back to the original problem of dropping points in this circle and square, we were looking at this function and we were using data to approximate this function. We were trying to learn that function through data. And, you know, you might be like, well, who cares? I have pi r squared. But this gets really interesting is, what happens if my circle's not such a great circle anymore? What happens if it's starting to break down over time? What happens if it's starting to deform? My data-driven approach is still going to give me an excellent model, an excellent representation of the area of this circular shape, where the original physics-based model is not going to work as well. And that's going to continue as the quote-unquote, the circle ages and decays, its performance decays, let's say. And now, one of the interesting games, we can actually extend this metaphor even further, and we can say, well, if we look at one particular circle and its pattern of decay over time, and we call that at a particular time t, the function g gives us the area of the shape, then can we collect data, enough data, to build a data-driven model to predict what the area of the shape will be at a certain time in the future? Could we build a model to do the same thing with the performance of a transformer? The answer is obviously yes. But then extending this further, what happens if we have n circles and those shapes are slowly decaying over time? can we use that data collected from all of these different circles to learn models applicable to my entire suite of or fleet of assets? And the answer to that is yes. And that's why everyone here should be really excited about how AI is going to not just immediately transform the grid and utilities, but how the utility of the future will likely not look much like the utilities of today as the assumptions underlying the cost of prediction change over time due to AI. That's all that I have. Thank you very much.
Okay, can you see my screen?
We can.
Great. So hi everyone, I'm Mohini. I'm a PhD student at Berkeley and I work mainly with micro-PMU data, which is high resolution phasor data from distribution networks. And today what I wanted to talk about was to talk about a particular use case that is enabled by the NI for AI platform. And I hope that this will give you a sense of how easy it is to use the platform and to query and analyze the data, and also get you started thinking about your own use cases and applications. And the particular use case I'm talking about is voltage sag detection and analysis. So as you've probably gathered from the previous speakers, the great advantage of this platform is that it makes it really easy and even enjoyable to explore data, including very high resolution measurement data that can be quite intimidating just in its volume, and especially if it's being shared in other forms, like in a CSV. And the platform not only makes it easy to explore the data, but it also makes it easy to analyze data and to ask and answer questions of the data. And finally, it makes it easy to share results, whether that's in the form of raw data or scripts or anything like that. And I think the last part of sharing results is often overlooked, but this is really essential if we want to effectively share knowledge and if we want to build on the results of others and ultimately deploy real applications. So what I'm going to do here is demo the typical development process for one use case application, and that's voltage sag detection and analysis. And I'm going to walk you through the typical 4 steps that I can think of for analytic development in this particular case. So in step 1, we establish our motivation for this particular use case and the questions that we have. So we want to answer the questions, what are we interested in understanding and why is this important? Well, in this case, the what is voltage sags, and these are brief, significant dips in the system voltage. And what we specifically want to understand about sags is their frequency and their magnitude. And why we want to understand this is because sags can have a detrimental impact on the system, especially on sensitive equipment. And they could also indicate safety issues such as faults in the network. So here are 2 pictures that relate to the what and the why. The first picture in the top relates to the what, and it shows us a voltage sag. And this voltage sag is captured in point-on-wave data. So that's measurements of the time domain voltage signal. And we can see that the voltage sag appears basically as this reduction in the amplitude of the sinusoid. And the bottom picture relates to the why. Why is this an important thing to monitor? And what it shows is the tolerance of a piece of equipment to deviations in the system voltage. And the green region represents tolerable deviations. And what we see is that it constricts over the x-axis, so it constricts with duration of a deviation. And essentially what this means is that a piece of equipment can tolerate large sags if they are short, or it can tolerate long sags if they are very small deviations from the nominal voltage. And so really what would be concerning in the system is a very long and a very large sag. Okay, so now we've established our motivation. We can move to step 2, which is to explore them. And it's really in data exploration that I think the NI4AI platform really shines. And exploration is very critical for the development of new use cases and analytics. So oftentimes we get ideas from looking at the data, and these are ideas that we didn't have to begin with. And it's really difficult, in my experience, to develop an analytic blindly, that is, without seeing the data at all. So exploration is especially important for two reasons. The first is that we may be working with novel measurement types, which we're not very familiar with. So in the bottom left, we can see that novel measurements really make a difference in what an event looks like. So we see the same event in SCADA data, which is lower resolution, and then in high resolution PMU data. And we see that the event really looks different in these two data types. And so therefore, we really need to explore the data to get familiar with what new measurements look like. The second reason exploration is important is that we may be looking at new event types, things that we've never seen before, or things that have just been made visible by higher resolution data. So here we have on the right some voltage sags in higher resolution PMU, micro PMU data, and we may not have ever seen this before in our lower resolution data. So those are two reasons why exploration is very important. So for this particular use case, I want to explore the data to understand what a voltage sag looks like. And what I really want to understand through this exploration is how can I automate the detection of voltage sags? Now, what I'm showing here is the Ping Things plotter, the visualization part of the NI4AI platform. And in this visualization, I can very easily find sags because there are these very distinct deviations in the voltage magnitude. And especially large sags are easy to see. And once I found a sag, I can quickly zoom in to look at it at much higher time resolution. So I can go from hours to seconds very quickly and really familiarize myself with the shape of these events. So looking at these sags, I understand that what I should really be looking for to detect sags is large deviations in the magnitude of the voltage from nominal. So that takes me on to step 3. So in step 2, I've got an idea of what I'm looking for and how I should look for it. And now I can automate the sag detection. And I'm going to do this in a Jupyter notebook, which Chris also showed you. And the great thing about the Jupyter notebook is that I can intersperse text and code and visualizations and really have a record of my work and exploration. So based on what I know about sags and based on my exploration of sags, I see that this sag, a voltage sag, is defined by voltage measurements below a certain threshold. And I'm going to develop an algorithm to detect sags in 2 parts. So in the first part, which I'm visualizing on the left, I'm going to find any points belonging to a voltage sag. So any points where the voltage is below a threshold that I'm going to specify. So for example, for this sag shown in red, in this first part, I'm going to return the set of points, all these gray points that are below my threshold. Now, after finding these raw points, I'm going to have a second part of the algorithm, which is going to aggregate these raw sag points into individual independent sags. And once I've aggregated these points, I can then determine the duration of the sag and its magnitude. So the reason I choose to construct my algorithm in these 2 parts is based on the structure of this very high performance database that's underlying the NI4AI platform. And this is what Chris introduced you to. And basically the main feature of the database is that it's structured like a tree. So at the bottom, in the leaves of the tree, I have raw data points. And as I move up the tree, I have these internal nodes that store these summary statistics of the raw data that lies below them. So this includes the minimum and the maximum of the data below that node. And as I go up in this tree, I'm getting to lower and lower time resolutions. So if I'm looking for extreme values, which is what I'm looking for when finding voltage sags, this structure makes it really efficient. I can look at a kind of large window, at the summary statistics over a large window, and consider the minimum in that window. And only if the minimum meets my criteria of being under a certain threshold only then will I go down all the way to the high resolution raw data to retrieve the voltage sag. Okay, so what I want to show you is this video where I'm walking through my notebook, which contains the scripts to do this exploration of voltage sags. So let me play this. So just like Chris's notebook, I start out with some basic imports of the database and of the different Python libraries that I'm going to use. And this is the great thing about being able to query the data into Python. I can use all these great libraries that other people have made to really speed up my analysis. Then I connect to the database, which is very simple. I use my API key, which all of you can get by signing up for the NI for AI platform. And now once I'm connected, I can look at the different data streams in the database very easily. So in this case, here I'm querying a set of streams. And what I'm looking for specifically is streams belonging to this particular collection called the sunshine dataset, and I'm looking for voltage measurements, so voltage magnitude measurements. So I run that. It takes just a second, and now I can print the set of streams that it retrieves, and these are the set of streams that I've got. So I have this whole streams in the sunshine data set of voltage magnitude measurements. They correspond to multiple phases at several PMUs. And notice in these notebooks, I can intersperse text like this with the code, so I can explain my steps and my reasoning through this use case. So here I have the first part of my algorithm. So this is the function that is looking for those raw sag points. And you see that and I call this find vsags DFS, it's a depth first search function because it's looking through this tree structure efficiently to find those sag points. And the arguments to the function are just my start and end times that I'm going to be looking over. And this is the point with which Chris discussed. It tells me the kind of resolution, the level in that tree at which I'm going to be looking for some data. So the function is not very long. It basically queries some windows. These contain the statistics over these time windows, the summary statistics stored at internal nodes in the database, and this query is therefore very efficient. And then I'm traversing the windows to find either points or windows that meet my criteria of having voltages below a certain threshold. And you can see here that when I find those points, if I'm at a low resolution, I now go down in the tree. So I'm going into higher resolutions of data to find the voltage sags themselves. And if I'm already down at a very high resolution near the raw data, then I just return the points themselves. So these points are pairs of timestamps and values. And then what this function ultimately returns is a generator or an iterator of these raw sag points. So every point returned by this function meets my criteria of being below a certain threshold and corresponding to a voltage sag point. So that is the first part of my algorithm. I can run it. And now the great thing is once I've written the script, I can immediately test it on real data. And so here I'm testing it on 1 month of data, 2015, and I'm going to try to find a bunch of raw sag points over this 1 month. And I'm choosing a threshold of 0.9 of the nominal voltage. So that ran very quickly, if you noticed. And now we can look at, for example, one of the sags that was found, and it's retrieving the data of the sag, and there's that sag. We see that it's this very typical large deviation from the nominal voltage. So now that I finished the first part of my algorithm, and this is the second part. So this function is going to aggregate the raw sag points into individual independent voltage sags. And what it's going to return is basically the start time of the sags that were found, their duration, and their magnitude, which is the magnitude of the deviation from nominal. And the input to this function is the output of the previous function, which is this iterator, or generator over the sag points. So now what I'm doing is I'm looping through those raw points, and I'm basically checking if a new raw sag point belongs to a previous sag or corresponds to a new voltage sag. So if the raw point is more than 1 second away from the last sag point, then I decide that it corresponds to a new voltage sag, and I store the summary of the previous sag and increment to start looking at a new voltage sag. And on the other hand, if the new sag point belongs to a sag that I've already seen, then I simply update my values for that sag. I increase its duration and adjust its magnitude. So I wrote that function and I run it, and now I can, again, immediately test it on a significant amount of data. So what I'm going to do is I'm going to test it on 1 month of micro-PMU data. So this is a large volume of data. This month corresponds to the end of 2016. And I'm choosing a more aggressive threshold of 0.98 of nominal to really get more voltage sags during this period. So I run this, and it's looking over that month, and we see that it's running. I see that asterisk in the top left, and now it's done. It's finished running over that whole month. It took just over 7 seconds, and it found 4 voltage sags. And what I can look at immediately is some statistics of these sags. For example, I can plot their duration versus magnitude of these sags, and I see they're distributed in that way. Now I can run it on an even larger amount of data if I really want to find more interesting sags. So now I run it over 3 months of data. Again, keep in mind, this is 120 hertz micro-PMU data. So this is a very large volume of data, and I'm looking for sags over 1 PMU stream. Now notice I've chosen an even more aggressive threshold. Anything below 0.99 of nominal, I'm going to return. And so here is the first part of my algorithm. This is the function that's returning the raw sag points. And then I have the second part of the algorithm, which is returning which is aggregating these points into independent sags and return the start times, their durations, and their magnitudes. So we give this a few seconds to run. And of course, I've chosen a very aggressive threshold. In a real application, you would adjust that based on the sags that are of interest to you. So now it finished running and it found a bunch of sags, and I can again look at their duration versus their magnitude, right? This is of interest because it reflects how equipment may react to the sag, and I see that they are scattered in this way. And I go on lots of different analysis with all these sags that were found. So I'm going to share that with you in the slides. Okay, so this is what I showed you before. Here I have an example of a voltage sag that was found by my algorithm. And now I move on to step 4 of the analytics development, which is to answer questions that I have based on what I found out from the data. And so some questions that I have about voltage sags are, what are the magnitudes and durations of voltage sags at this particular location? How well does a model from the literature describe the frequency versus magnitude of the sags we observe? So as I said, the magnitude of the sags is important because it indicates how equipment may respond to these sags or how damaging they may be in our system. And we have a model in the literature that will describe the frequency of sags of a certain magnitude, and I want to validate that model against the data that I have. Another question I have is, do we see any impact of distributed generation on the sag magnitude? And finally, are there any weekly patterns in the sag frequency at this location? So I'm answering all these questions in my Jupyter notebook using those voltage sags that I found with my algorithm. And this is in answer to the first question: what are the magnitudes and durations of sags that occur at this measurement point? So I see here's a scatter plot showing the duration of the sags on the x-axis and the magnitude, the deviation from nominal, on the y-axis. Or sorry, rather the magnitude shows the minimum value in the sag in per unit on the y-axis. So these here at the bottom are much larger sags. And these sags were found over 1 month of data, so that's 300 million data points, and it ran very quickly. You saw that in the demo. So the interesting thing here to note is that I don't have any sags in the danger zone in this region, which is good. So on this system, I didn't see any large and long sags. So that's great news. Okay, so on to the second question. How well does a model from the literature describe the frequency versus magnitude of the sags we observe? So in the literature, there's this very simplified model, which makes a lot of assumptions, but tries to model fault-induced voltage sags and to predict the frequency of sags of a particular magnitude. And basically what this model says is that the frequency of a sag with magnitude V will be proportional to V over 1 minus V. So what that means is that we will have far fewer very significant sags and far more small sags from nominal. So the orange line is what the model would predict, this simplified model, and the blue is from my data. And what I see is that it looks pretty promising. Of course, I would need to do more analysis at more locations to say that definitively, but this model fits this location over the time period that I looked at quite well. Okay, on to the next question. Do we see any impacts of distributed generation on sag magnitude? So there is some theorizing in the literature that distributed generation, the presence of distributed generation may reduce the magnitude of sags at a location because the injection may hold the voltage up during a sag. And we can explore this through the platform because we have access to an open source database which includes measurements at an injection point of a PV installation. And so that is in the Sunshine dataset, which you can all access. And basically in this dataset, we have a PMU1, which is measuring at a PV location. We have another PMU at the substation above that PV injection point, and then we have PMUs further away on other feeders. And so now I ran my sag detection on all these PMUs, and I can look at the magnitude versus duration at each of those PMUs. And the stars correspond to the means at each PMU. And it does look like from this small experiment that the sags are smaller on average at PMU1, at the PV injection site, than at the other PMUs further away. Finally, I can look at the frequency of sags over days of the week and ask about whether there are weekly patterns in the sag frequency. This is made very easy by the platform because I can work easily with the timestamps on the measurement data and do this analysis. And at 2 different PMUs, I do see that there is some very distinct days on which I have more sags. That was the extent of my analysis of this. Of course, you could do more analysis to find out why that may be the case. So after answering all those questions and going through the steps of the use case development, the last step is to share my results. And in fact, the great thing is that this is very little extra work because I basically have something to share right away as the output of my analytic development. And that is the Jupyter Notebook, which has this code and text and images mixed together. And it's something which is very readable and which somebody else can run and add to. And that's all from me. So I'll stop sharing.
Great, thanks, Mohini. We got a couple of questions in the chat window. The There's one that says the example demonstrates voltage sags. Hold on, it's a long question. Voltage sags show to be find voltage sag events for a simple report. This is focused on one phase at a time. The question is, could this be extended to study three-phase faults?
Yes, absolutely. In the sense that we do have three-phase data at these PMUs in that data set. So you could look at measurements across the three phases.
And there's another question that says, is it possible from the magnitude and the duration of the sag to predict the cause?
Perhaps I wouldn't be able to from just this data, but perhaps on certain systems, somebody familiar with that particular network would look at a sag and maybe from its shape or the time it occurred, be able to say something about when it occurred. Also, if you had enough data and you had historical data, you could probably discover those things through AI kind of techniques.
There's another question about the slide with the data organization structure. You mentioned that as we move up the tree, the resolution of the data, hold on, here, there are more questions coming in, sorry. The resolution decreases, and as you move up the tree, the resolution decreases, and only the statistics are stored instead of the time value points. Could you speak a little bit more to the structure of the database and the organization of the data, the stat points?
Yes. So the data is organized in this tree structure. So at the bottom, I have the raw data points. And then as I move up the tree, I have the summary statistics over increasingly large windows of data. So for example, the topmost node would contain the mean, the min, and the max over and the entire set of data. And then as I move down, I'm getting those statistics for smaller and smaller windows. So I do have a time point associated with those internal nodes, or rather two time points corresponding to the start and the end of the time window under that node. And then as I go all the way to the bottom, I have a value associated with a single timestamp. And the database underlying the platform is the Berkeley Tree database. And if you look that up, you can find out more about the structure.
Great, thank you. There's another comment that I'll just read. It says, in regards to the question about cause, you do need a lot of context beyond the magnitude and the duration to understand what caused an event.
Yes, exactly.
Okay, with that, I'm going to make Miles the presenter.
Hello, everyone. Okay. Can you see my slides?
We can.
Great. Okay, so now we are going to talk about another parameter of power grid systems, a state variable, which is frequency, and phase, which is very related to frequency. Frequency is, I think, a concept that everyone feels they understand well. And on the power grid, frequency corresponds physically to the rotation of large magnets in generators, synchronous generators that are powering the grid. And so we can model this rotation as a sinusoidal function with a magnitude, and Mohini just covered voltage magnitude. but there's also the argument of the sinusoid. And so here I'm breaking down that cosine argument into two terms, omega naught times t, which is omega naught being the nominal 60 hertz frequency on the grid, and then phi, which is the phase of this oscillation. And it's important to understand that phase only has meaning when you're comparing two sinusoids. So in this image, we can see that these two ideal sinusoids, cosine and sine, are separated by a phase phi of 90 degrees. And so and we can visualize that in the phasor diagram on the bottom picture. However, this phase definition, this simple phase definition, really is only meaningful and well defined for ideal sinusoids with constant frequencies. And you can imagine asking yourself, what is phase for two sinusoids at different frequencies, where for every moment in time it seems like the apparent phase between them is changing. So for that case, we will we'll add some complexity to our functional form of the voltage waveform, and allow the magnitude to vary with time, which Mohini illustrated in her talk with voltage sags. And we also will allow this phi term in the argument to vary with time. And then we can define the frequency as the time derivative of the argument of this cosine. And so in the bottom, we see that under that definition, the frequency would be omega naught, which is the 60 hertz nominal frequency, which is constant, plus this d phi over dt term, which actually does vary with time. And this d phi over dt gives us the all the complexity that we see in real data on the grid. We can also, what is often done is we subtract out the nominal frequency term, because since it's constant, it's not very interesting to us. And then we're just left with this phi of t term, so we can then define the omega of t as the time varying frequency deviation from nominal. And so let's show think about some examples of phase in different situations. So in this top row, we have time, like a waveform of a signal in time. And so remember that the phase needs to be defined between two sinusoids. So in this case, the reference sinusoid that we are using to define the phase is a perfect 60 hertz sine wave. So on the top row, our signal is also an ideal sine wave of 60 hertz. However, it is phase shifted from from our reference sinusoid. When we calculate phi of t, in this situation, we're going to get that it is non-zero but constant. And when we take the derivative of phi of t to obtain frequency, we're going to get that the frequency is 0. And this makes sense because what we really mean by omega is the frequency deviation from 60 hertz. So since our original signal is at 60 hertz, it makes sense that omega is 0. Now, in this bottom row, now our sinusoid signal that we're measuring is slightly, has a frequency that is not 60 hertz, but slightly larger than 60 hertz. And what we get from our definition of phi of t is that it is linearly changing with time because the frequency of our signal is constant, but different than 60 hertz. And so in that case, when we calculate the derivative of phi of t, we get a constant frequency that is greater than 0, which means that our frequency deviation from 60 hertz is greater than 0. So our actual frequency is slightly larger than 60 hertz. So now let's look at some real data. And so this data is from the Sunshine data set, which was mentioned earlier. And just visualizing what we see, we notice that the phase is constrained to be within 0 and 360 degrees. And this makes sense based on our sort of understanding of phase angle, where an angle is usually between 0 and 60 degrees. However, this creates some problems when we want to do computations using this phase, because let's say we want to actually take the derivative to obtain frequency. Part of that process is computing a discrete difference of phi of t. And we see in the bottom plot that this discrete difference has these very large artifacts that occur every time the phase jumps from 0 to 360 degrees. And so these artifacts are not physically large jumps in frequency, and so we need to remove them to see the actual frequency signal. And so to do that, we're going to unwrap the phase. And what that means is remembering that angles are relative. And so an angle of 0 is equivalent to an angle of 360. An angle of 10 degrees is equivalent to an angle of 370 degrees. And so when we see a zero crossing of the phase, we can add or subtract 360 degrees and still have the same angle, but remove the discontinuity that's present in the data. And so we can do this with a relatively simple function. And what this function is doing is it's assuming that these discontinuities in the phase are significantly larger than the other differences between consecutive points. And which is a good assumption looking at this plot of the like initial difference. We see that actually we can't see any variation around other than these large artifacts. So we define a threshold that is going to be between these discontinuity, the value of these discontinuities, which in this case, the value is going to be very close to 360 degrees. And so we can define a threshold that's maybe 350 or 300. And when we detect a change that is greater than our defined threshold, we assume that we've encountered a discontinuity and we either need to add or subtract 360 degrees to remove that discontinuity. So now we're going to use these tools that we've developed to look at a case study, which is the Blue Cut fire, which happened in 2016, August 16th, 2016, in Southern California, and it caused a transmission line fault, which caused a drop in frequency that caused large solar farm inverters to trip offline. And so looking at our sunshine data set, we see that we do have data on this day. So that's exciting, and let's check it out. Let's look and see what we find. I've gone through all the steps that have been talked about earlier on, like how to query the database and obtain this data. And then I've unwrapped the phase so that we see this continuous phase evolving. And then now we can take a derivative and we get this graph of frequency. And there's a few things to notice. The frequency displayed in this report of the case study, of the report of the Blue Cut fire fault, looks very different than this frequency initially, and we'll like explore that. Another thing to note is that what isn't apparent, or taking the derivative to obtain frequency, has introduced a lot of high frequencies in the outputs, which weren't completely apparent in the phase plot. So a very common method to deal with this introduction of high frequencies is to use a low pass filter to get a better signal. And so here we are with the same plot of frequency, just visualizing a part of it during nominal functionality. Zooming in, we see that the frequency is just under 60 hertz, and it's varying quite a bit. And let's zoom into this large spike, which is due to the Blue Cut fire fault. And we see that a few interesting things. So this graph is actually plotting 4 different PMUs at different locations on a distribution network. And we see that these PMUs disagree on what the frequency is during this anomaly. We also see that there's overshoot in the frequency signal. And this overshoot occurs at a very short time scale, a time scale much shorter than like you would see from an actual controller that is controlling the generators that are actually causing the frequency. So that those two facts lead us to believe that we are seeing some errors or artifacts in the that's coming from the signal processing internal to the PMUs themselves. So here we're just visualizing on the bottom the graph that's reported of the frequency faults during the blue cut fire, and our data, which they look quite different. So what we're going to try to do is apply a low pass filter, specifically a moving average filter, to smooth out this high frequency noise that's been introduced by taking the frequency. And so to introduce the concept, or to explain the concept of a moving average filter, let's look at maybe some plots that many of you have seen following the news. And we see here is from the New York Times, a graph of daily COVID cases. And we see that on a day-to-day basis, there's quite a lot of variation, but you can take a 7-day average and get like a smoother line. So we're going to do something very similar to that, but it's not going to be on the scale of days. It's going to be on the scale of seconds. And so here we are applying two filters, two moving average filters to our data. And if our window length is exactly 0.1 seconds or 100 milliseconds, we see that that doesn't provide very much filtering, and our data looks very similar to the raw data. But if we apply a 0.5 second average to our data, we lose the overshoot that we're seeing in the first plot, which is promising because that overshoot is likely not due to a physical process. And we also see that after applying this filter, our data now resembles the frequency data reported from the blue cut fire. So I think this is a very exciting case study that shows that this data is real, and that it illustrates that frequency is largely a global variable across the grid. So even though these PMUs on the Sunshine dataset are at different locations, they're all reporting a very similar frequency trend that agrees with the frequency from this fault. And so a few conclusions. another point is that frequency is not really well defined during transient events, because during these transient events, the waveform isn't really sinusoidal for a brief period of time. And the PMUs are, ingesting point-on-wave data and fitting that data to sinusoidal function, which works well when the point-on-wave data is about sinusoidal or nearly sinusoidal. But during these fault events, that fitting algorithm is now operating under, or the assumptions it's operating with are being temporarily violated. So there is likely going to be some frequency error during these transient events. There is an IEEE standard that requires PMUs to have errors within certain bounds, but the specific algorithm that these PMUs need to use is not specified, and these algorithms are often proprietary to the companies making the PMUs. It's, I think, good to remind ourselves that point-on-wave data will be most accurate during these transient frequency events. And so that's all I have, and happy to answer any questions.
I wanted to close by saying thank you again for taking the time to call in today. We hope that you found the content of this workshop to be interesting and valuable to you, and that it was inspiring enough for you to go home and start using the platform and using the data in your own work. If you have any questions at all, please feel free to send us an email. We would love to hear about the work that you're doing, about data that you're working with, or would be interested in having us host. And if you're interested in hosting a sensor for us to stream data into the platform, we would be happy to engage with you on that as well. I want to say a final thank you to each of our panelists for their work in putting together talks for the workshop today. And we look forward to hearing from you in the future, and we'll all be available for live Q&A during the SmartGridComm agenda in a couple of weeks.